Uh, so last day we discussed about finding lower bounds of some algorithms. Okay, so hope you can remember all the techniques that we had used. So today we'll discuss another approach to find the uh, lower bound for some kinds of algorithms. So actually there are some problems where you may not be able to apply the direct technique to find the lower bound. Then we have some another kind of technique which is known as linear time reduction. Okay, linear time reduction, which is another type of or another kind of approach to obtain the lower bound. So because again there may be some problems to find the lower bounds for different kinds of problems. So then we may apply this approach where we can convert one problem to its corresponding another type of problem. Okay, and that is known as linear time reduction. That means we are reducing one problem to another problem. Okay, let us go for the formal definition of what is the meaning of linear time reduction. After that we will go for one example. Okay, that I think that will be clear to you. So now let there is a problem A whose lower bound is known. Okay, that may be anything which is a function of fn. So it may be omega of n or omega of n log n or something like that. Okay, omega of n log n, anything, any function of n. So mind it, there is a given problem A whose lower bound is known to us, and let the lower bound of the problem A is given as omega of f of n, where fn is a function. Okay, n is a small o of n. So that means it may be greater than n, but the lower bound or the tight upper loose upper bound of n is small n. Okay, small o of n. Then we want to find the lower bound for the given a problem B. So let B be a problem for which we wish to establish a lower bound. Now our target, since we know the lower bound of A but we do not know the lower bound of B, so our target will be to find the lower bound or to establish the lower bound which is equivalent to a function of f of n. Okay, omega of f of n. So A is a given problem whose lower bound is known to us. B is a given problem whose lower bound we will find, and we will try to find such that it is a function of n or f of n. Which f of n? The function which is providing us the lower bound for capital A, another problem. Okay. Then how? We establish the lower bound of B as omega of fn by following some steps. What are the steps? First, we will convert input A. So that means when a problem A is given to us, there will be a set of input. Okay, that is, an input will be there, and we will apply the algorithm A to, not the algorithm A, this is the problem. We will apply some algorithm to generate the output. This is the process. Okay, so this is the problem, this is not the algorithm, sorry. We will apply an algorithm here to produce the output. Now the time complexity of the problem A is given as omega of f of n. This is given. Our target is to find the time complexity or the lower bound, not the time complexity only, the lower bound complexity of the problem B. So first, what we will do, we are having a set of input for A or input set for A. Now we will try to convert the input set A into a suitable input to the problem B. Think about that. So let input, let I1 or IA is the input for the problem A. What we will do, we will try to convert this IA to the input set of B, which is known as IB let. So our target will be to convert IA to IB. So that means input of A will be converted or to a suitable input to the problem B. Okay. Then what we will do? We will solve the problem B. Then we will solve the problem B, and obviously we will get some output by solving the problem B with the input set IB. Think about that. So what we will do? First we will convert the input set for A to the corresponding input set of B by following some method. Later I will come that what should be the method. Then we will solve the problem B with the input set IA, which is converted to IB now. Then we will get some output of the problem B. Then what we will do? We will convert this output say to the output of A. Okay. So again I am repeating because this is a little bit conceptual thinking. So, and please try to visualize that what we are going to do. We are having a problem A whose lower bound is known to us. We are having a set of input or input set which is the input set for A. Now first we will convert this input set of A to the input set of B. Then we will solve the problem B. We will get an output for the problem B, and then again we will convert the output of B to the output of A. Okay. So this is known as reduction. So what we will say? We will say that A is reducible to B. Okay. This concept again we will use whenever we will discuss the NP, that is P or NP. I think you have heard of this, right? The different types of algorithms, P, NP class and all these. Okay, NPC. So actually it is known as non-deterministic polynomial time. So later we will discuss, but that time again this concept will be required. So try to memorize this very clearly and try to understand this property very clearly. A problem A is given, we convert the input of A to the corresponding input of B, we find the output of B and then convert it to A. So here if it is possible, then we will say that A is reducible to B. Clear? A is reducible to B. Now if all these three steps can be converted in linear time, that is which is a function of n. If all the three steps can be converted or can be executed, all the three steps can be executed in linear time, then we say that this reduction is a linear time reduction. So now we can write that A can be linearly reducible to B. A is linearly reducible to B if all these three steps can be executed in a time complexity n, which is known as linear. Okay, right? So a problem A can be reducible to B if we follow these three steps, and this is known as linear time reduction, reducible if it can be reduced in a polynomial of n. So we say that A has been reduced to B in linear time, and already I have written that this is denoted as this. Okay. So from here what we can do, think about that. Now if A can be reduced in linear time, and if the lower bound f A is given as omega of f of n, then we can say that the lower bound of b is also a function of this. Think about that. A, if A is linearly reducible to B, and if the lower bound of A is known to us, which is given as big omega of f of n, then we can say that the lower bound of B is also omega of f of n, right? So in this way, we can apply the linear time reducible approach to find the lower bounds of some algorithms. Let us go for one example, and I think that then your concept will be a little bit clear. Okay. So let us find the lower bound of the convex hull problem. I don't know that how many of you are having the idea of convex hull. So if you have the idea, then it is fine. But still, let us for recapitulation, or we can go for another discussion. Okay. So today I will give, it is in your syllabus, here to find the lower bound for convex hull problem. But as per my thinking, it should come after the discussion of convex hull problem, which is given at or within the branch and bound algorithms like that. So still, since it is under the topic of lower bound founding algorithms, so therefore let us go for a brief discussion of convex hull problem. But our target is to find the lower bound for the convex hull problem. Our target is not to discuss the convex hull problem and its solution, but since we have to find the lower bound for the convex hull problem, therefore we need some idea of the convex hull problem. That's why I am discussing with a small example. Okay. Now, what is a convex hull problem? The convex hull of a set Q is a set of points which is represented as, say, xi and yi. Okay. Let Q is a set of points. Let Q is a set of points whose coordinates are given as xi, yi. Let there are a number of points in the set. Okay. So x1, x2 up to xn, like that. The convex hull of this Q is given as, let CHQ, okay, CHQ, which is the smallest convex polygon. So what is CH? CH is the smallest convex polygon. Listen it very carefully. P, for which each point of Q, each point of Q or each point in Q on the boundary of P or inside its interior. Okay. So what is a convex hull? Convex hull is the smallest convex polygon P where each point of Q is either on the boundary of P or inside its interior. Let us go for one example. Let we are having some points like this. So how to find the convex hull of a set of points? There are two algorithms. Again, I will discuss this in detail during our branch and bound topic, but just for a brief discussion. So we are having two different kinds of solutions or algorithms to solve this convex hull. One is Graham scan, and another is Jarvis merge. Okay, another is Jarvis merge solution. So one is Graham scan, another is Jarvis merge. So The time complexity of Grimes scan is big O of n log n, and the Jarvis march is big O of n into h, where h is the number of vertices, okay, in CHQ. So before going to the Jarvis march, let us briefly discuss the Graham scan. Okay. So how the Graham scan finds the convex hull? This is like this. So first, what we will do? We will sort. First, we will select one point. Select the point. Let P0 with lowest y coordinate. Okay. So first we will find the point whose y coordinate is the lowest among all the points. If there are 2 points or more than 1 point with the same y coordinate or the lowest, then we will go for minimum x coordinate. Okay. So there will be no controversy. First we will select a point P0 with lowest y coordinate. If there is any duplicate value, then we will choose the minimum x coordinate among all these. Next, for the other n minus 1 points, what we will do? We will sort all the elements, all the points according to its polar angle. Okay. Sort all the points according to its their polar angle. Then we will apply the algorithm to find the convex hull of this. So let us go for an example. So think about that this is the coordinate axis, x-axis and y-axis, let we are having some points. Let us consider this is P0. Okay, you can consider any other thing, any other point. Let this is P0, mark it, and we will consider this is the minimum y and minimum x among these. Okay, minimum x may be not that, but minimum y. Then we are considering few points, maybe like this. Okay, say we want to find sum of we want to find the convex hull of this point. Then what to do? It has been said that we will sort all the elements except this P0. We will sort all the elements according to their polar coordinates. So this is let P1, this one is P2, okay, so this one is P3, then P4 and so on. Okay, or it may be let us consider another one. Let this is here, then I think it will be a little bit clear. So this is P2, this one is P3 and so on. This is P4, P5, P6, P7 and P8. So all are given. So this is P2, P3, P4, P5, P6, P7 and P8. We have to find the convex hull of all these points, and these are sorted. Okay, theta 1, theta 2 and all these, right? So you have to find the convex hull of the given point. So what to do? First, we will connect P0 with P1. Okay, since there are only 2 points, so we have no problem to connect all these. First, we will connect P0 and P1. Then what we will do? Now these two are connected. Next, we will connect P1 with P2 and check. Sorry, we can connect P0, P1 and P2. So we will use a stack here that will consider P0, P1 and P2 as the input. Okay. So initially we have connected P0 with P1 and P1 with P2, and we have pushed these three elements onto the stack. Then we will try to connect the P3 point with this. Okay, so mind that this is the convex hull that we are trying to create. This is connected. Then we will check that whether P1, P2 and P3, that means whenever we are considering the new element P3, we will check whether the P3, P2 and P1 is creating a non-left turn or not. Okay. So our target is to find whether it is creating a non-left turn or not. If a non-left turn is being created, then we will remove the topmost element and insert the new element. Okay. So here please check. P0, P1 and P2 are connected. So which are within this. Next what we will do? We will connect this element here, P1, P2 and P3. Now check, this is a non-left turn, that means right turn. Okay, non-left turn. So immediately we will remove this P2 and insert this P3. What does it mean? That means now we have connected this P3 here, and this one will be removed, because if we connect, think about that, if we connect this, then P0, P1 and P3 automatically will contain P2 here inside this. Okay. Then next we will check that whether P4, P3 and P1 is, that means the new, now it is P3. So new entry P4 is this one creating. Okay. So whether it is creating a non-left turn or not. No, this is a left turn. So therefore what we can do, we can connect this here. So that means now P4 is within the stack, right? Then again we will check P5. Now think about P3, P4 and P5 is connected. Okay, because it is again a left turn, right? So on our stack P5 is there now. Now if we connect P4, P5 and P6, this one is 6, what we are getting? We are getting a non-left turn, that is right turn. Okay, immediately we will remove this P5 from our stack. We will remove this P5 from our stack and we will insert P6 here. Okay, what does it mean? That means we are connecting this. Okay, and we are erasing this one. So here P5, this point is there. Similarly, we can connect P7 and this is a left turn, there is no problem. Then P8, left turn, no problem, and P8 to P0. Okay. So now think about that, all the points P2 and P5 and are within this interior, and all other points are on the boundary. So this is the convex hull which is generated by the Graham-Scan algorithm. Okay. And Jarvis march is nothing but the same, more or less same, which is saying that you consider a rubber band or a thread, okay, stretchable thread, and nail it here at the first point P0, then you move this anti-clockwise, okay, then you will get this P3 marked, then again you turn this P4 marked, then you turn this P6 marked, then P7, then P8 and so on. So these are the vertices of the convex hull, and the Jarvis march says that it will take time n into h, which is again if the number of the term is nearly creating a tree which is order of log n, then the time complexity is nh can be equivalent to n log n. But the gram scan algorithm is properly n log n. So this is the solution for finding the convex hull problem. Now the question is that what is the lower bound for this? This is the upper bound, maximum time that can be taken. This is fine. But whether the lower bound is n log n or not, that means is there any method whose time complexity is less than n log n to solve the convex hull problem or not? That is the main query. Okay. So this is not our target. Our target is that is there any algorithm, or is it possible to find an algorithm? Is it possible to find an algorithm whose time complexity is less than n log n or not? That is our target. Okay. Now let us check that whether it is possible or not. Here we will use the approach linear time reduction. Okay, we will use the linear time reduction approach to find the lower bound of the convex hull. Okay, so before that, we have already found the lower bound for searching algorithm, and we have also found the lower bound for sorting algorithm that we had discussed in our last class. So these two are known to us. So let us consider any comparison based sorting technique, and we know the lower bound for this, and we know that the lower bound for any comparison based sorting technique is order of n log n, big O of n log n. Okay. So what is given? Any sorting problem. Let us consider this is A. So an input set for any sorting problem is given. Okay, any sorting problem is given. So what is the input set for any sorting problem? This is just a set of numbers. Let us consider that all are integers. For the sake of simplicity, you can consider any number. So let 5, 7, 8, 16, 10 like this. So this is the input set for the sorting problem. Okay, let I. What we have to do? We have to convert this to an equivalent set of input for the convex hull problem. How to do this? The input set for sorting is a number, okay, but the input set for convex hull is a coordinate xi, yi. How to do this? So we can apply a function. Which will convert a point or a value to its corresponding x, I and xi square. We can do this. So that means this value, this array can be converted as a set of points. So this is 5, this is 25, this is 7, this is 49, this is 8, this is 64, this is 16, this may be 256, I don't know. This is 10, this is 100, and so on. Okay. So we can apply a function, any function, which will convert a point to, a value, an integer, to its corresponding x and y value. Right? So it can be converted to the input set of a convex hull problem, which is some points on the coordinate geometry. Okay. Now, what the time is required to convert this? N, because if there are n number of elements in the list, so just we are multiplying it with itself, and that will also take n number of execution, nothing else, not more than that. Okay. So first we will convert a point xi to its equivalent xi square, right? And then we will solve the convex hull problem by using Graham scan or maybe Jarvis search, merge, anything. So let us, for this we are considering Graham scan algorithm. So if we solve this Graham scan, this set of points by Graham scan algorithm, what we will get? You see, first we will consider the minimum value. Let this, the first one, okay. So if this, we can get 5, 25. So let us consider that this is the first point, okay, and we will sort all these elements as per the polar coordinate. Now if you plot all these points, you will get a parabola. If there are some values less than this, then also you can get this, okay. So you can get a parabola like this. So all the points here are on the boundary, which is also a convex hull, right? This is also a convex hull. It is not that some of the points must be within the interior of this. No. If all the points are on the boundary, then also it is a convex hull, because the definition of convex hull was that either the points will be on the boundary or within the interior. So if you plot these points, you will get a parabola. And obviously this is a convex hull for all these points. Okay. Now what to do? So we have first converted the set, input set of a sorting problem to the input set of convex hull problem. We have applied a solution for convex hull and we have found that a parabola is the output. Now, 3, the target is that this parabola or the points on this parabola must be converted to the output of a sorting. That means all the points must be in sorted order. All these points must be in sorted order. How to do this? Just you consider the points as per the minimum to maximum x coordinate, nothing else, okay, into max x coordinate. Then what will you get? If this is the minimum x coordinate, so I will get this one first, this is second, third, fourth, fifth, like this. So for this example, what you will get? 5, this point will come first, then this one will come first, then 10, 100 will come here, then, and see, all these are as per the y coordinate, sorry, x coordinate. So what is y coordinate? Y coordinate is the just the square of this. So if x is minimum, y will be also minimum among all these. This is the second minimum x, so this is the second. We go on finding or just listing out these points as per the minimum x to maximum x, what we will get? All the points are in sorted order, nothing else. Okay. So if we get all the points in sorted order, just we will discard these values, we will discard these values and we will discard all these values and we will consider only this. So we will get 5, 7, 8, 10, then 16 and so on. So which is the output of a sorting problem. So what we did, we have first converted the input list to its corresponding input for convex hull problem. We have solved the convex hull problem by using Graham scan or Jarvis merge. Then we have list out all the points by its minimum x coordinate. Okay, this one will come first, then next, and so on. So obviously all the points will be in sorted order, and which is the output A of any sorting problem. So here, sorry, here what we did, we have converted a sorting problem to The convex hull, n number of inputs were there, and that is in linear time. Okay, so we can say that sorting is linearly reducible to the convex hull problem, and since the lower bound of a sorting already you have proved that it is omega of n log n, therefore we can say that the lower bound of convex hull problem is also omega of n log n. Okay, so by linear time reduction, we can also prove or find the lower bound for some algorithms. This is another approach, right? So you have to keep all these points to find the lower bound, and also that why lower bound is required. If you have any query, you can ask. Otherwise, this is the end of today's class. Do you have any query? Hello?
No, sir.
No one is having no query. No one is having any query. Okay. So let us talk. Today I'll discuss the amortized analysis. Okay.
Okay, sir.
Okay, sir.